to you about Postgres, how we do it right now, very briefly, and then we'll more interestingly talk about how we envision Postgres on Kubernetes, why this is important for us. We will hopefully show you and convince you somehow that Postgres can run in Docker and also can run in the Kubernetes environment. What we are talking about is basically database as a service at Zalando. We'll briefly introduce the UIs and the monitoring we have right now, and then I will hand off for more technical talk to Alexi to talk about Patroni and the Postgres operator that is basically driving the future of the infrastructure. So let's take a look. About me, I mentioned it. My name is Jan Musler. I'm the engineering lead, which basically means I hand all the technical questions to Alexi later. And Alexi is an engineer in my team who has basically spent most of his work on Patroni and the operator recently. So I hope we can answer all your questions later. Zalando and Postgres at a glance, it basically means, and maybe some of you have heard that already before, that we run a lot of Postgres databases in the data center. Then AWS came along, and this was appreciated when you run something like database as a service, and everyone wants something else: bigger disk, smaller disk, faster disk, more memory, and so on. How's the state right now? Patroni is powering more than 150 production databases on AWS, running on EBS, running on local storage. Why this is beneficial, we can briefly cover later. And what's the interesting part is that we are transitioning hundreds of databases basically to Kubernetes. The reason for this is basically saving money, putting more resources to more efficient use, and also believing that the self-service we will show you later basically makes our life much easier in the database engineering team. Where are we coming from? We're running basically Postgres and LXC containers for a really long time in 2 different data centers spread across Germany. There was the Git repository with all the configuration that was cloned to the host, and then basically scripts were setting up the infrastructure. So this is always a good thing to do, have your basically configuration in Git somewhere, do pull requests on this. We had something called the Database Discovery Service already, so a REST API to find all the hosts and all the databases in production. This helps when you have automated monitoring and other tooling that basically needs to know on the fly where the stuff is running. What else is interesting, we always had the second data center basically at a time delay, like 1 hour of replication delay. This helps you a lot when you accidentally delete stuff, because the streaming stuff is really quick. Here it still shows we have Postgres 9.3 and plus, but actually very recently we migrated almost everything to 9.6. Thanks to PG upgrade and minimal downtimes, this is really beneficial to everyone. Performance went up and the people appreciate the new features also. Next slide. Briefly I mentioned this already. We have the Git repository in our local GitHub set up, and then we basically do push, pull, and so on, and then it gets deployed. Not so interesting anymore. Let's go briefly to Postgres on Amazon. I said already it makes our life very easy. We can much quicker provision databases than before, where we had basically to wait for hardware forever. And this is way more fun on AWS. And what does it mean? We have more memory, more CPUs, different storages available, so we can tailor this much more to the needs of individual teams. What also was interesting, that Docker was basically for compliance reasons basically in. So basically we needed to know what is deployed and where and which software. So basically Docker images were our deliverable. I think there was some fighting in the team initially. I wasn't in the team at the time whether Postgres is supposed to run in Docker, but I think by now everyone agrees this works quite well. We expected more node failures on AWS. Everyone told us EC2 is unstable. Turns out it's not the case, so the cloud is actually a lot of fun, and EC2 is pretty stable. It very rarely fails, and if so, you almost always get an email ahead of time. But this basically drove the team to build Patroni some time ago as a fork of Governor. And what it actually is, it's a Postgres management daemon that tackles the problem of basically bootstrapping and, more importantly, the automated failover, so no one basically has to get up at night. And while I joined Zalando 7 years ago, spent 2 years in the database engineering team and really had to wake up at night, when I came back in January 2017, seeing basically Patroni in action on AWS, it's pretty amazing for me to see how well this really works. It uses master election, basically backed by etcd, or you will later learn we by now use the Kubernetes API for this. Much more systems are supported. It's not pinned to AWS either, so it also works on Google and other implementations. It was one of the first open source repositories at Zalando with a growing adoption. The first basically non-Zalando contributors, which we really appreciate, people testing it on different platforms and giving back. This is the whole idea why we basically open sourcing this to make use of Postgres easy. So more about Patroni later from Alexi. Maybe one question, why are you not using RDS or why are you not using Aurora? There's nothing really bad to say about either of them. Aurora is also pretty interesting technology, and we think at a certain size it makes sense to use. But in the end, we believe that having Postgres, having it under our control, having a real super user, having streaming replication in and out of the system between different accounts, between data center and AWS, is in the end beneficial for us. The integration, we will show it also, is basically better. So we connect it to our IAM solution. We will show this. And we are also able to use local storage. And this is basically the main instance type we now use for everything that is requiring performant I/O. So we run thing on ephemeral i3 instances on AWS. This means we have like SSDs, and when the machine dies, everything is gone. But we have 2 replicas across availability zones, and we strongly believe that this is good enough for us. And until today, it has worked flawlessly. But let's talk about Postgres as a service. So why are we going to talk about this? Because former in the data center there was a Jira ticket. On AWS there was still a Jira ticket. And everyone who waits for a database like 2 days or so, he will go to RDS immediately. Why? Because there is a button and you have your database and you are done. So the whole idea basically when Kubernetes came to life beginning of 2017 was let's build something that is equally convenient to use. It makes it really give you a database within like 30 seconds in your cluster, make it easy to connect, provision users and so on. And you will see it later, this is basically what we have right now. So fast provisioning of Postgres databases or clusters in our infrastructure, connected to deployment pipelines, connected to our platform IAM. And let's look at how it looks like. Did I miss something? No. Yeah, so amazing UI work by myself and the team here. So everyone loves doing UIs in JavaScript. It's very powerful. Basically, you know this. You give this database a name, you select a version, 9, 6, and 10, and that's also the benefit. We have Postgres 10 rolled out. We're not waiting for Amazon to give us 10. What else is there? A number of replicas and so on. A replica load balancer so that you can basically do read load balancing. And then there's one point I will show later is basically user and database configuration. Why I will explain later. So let's click a button, provisioning, more provisioning, and database is ready. We are skipping the live demo, but basically this would take roughly about 30 seconds for provisioning new clusters. An interesting part that is in there, basically make it easier and especially hands-on deployments is about role provisioning. So we are supposed to not connect to databases in production, no SSH, no pSQL, nothing. So let's look at what we can do to make this really like hands-free. And this means like declarative user and database description with an owner and another role to connect your application. And then there's something nice in Kubernetes. I'm not sure. Let's make a show of hands here. Who is aware of how Kubernetes works a little bit or understands some stuff? Yeah, see, that's pretty amazing. The key part is that there is something called Kubernetes secrets, and you put credentials into this, and then you can use it in your application. And this makes the life for the developer quite easy. He doesn't have to worry about can he commit credentials in Git, do he has to use encryption and so on. It basically never leaves the system. And there's one example down here where it basically connects the whole thing, but this allows basically application deployment with a database created and roles, and then Flyway to kick in to provision everything you need without ever connecting to the database. And that is like the whole idea. So basically have a deployment pipeline on the Git repository with all the configuration and your application is up and running. Yeah, and the last one is basically encouraging this role split. I think more people here are aware of like good design practices than most engineers who just want to have a super user and do everything with this. So some idea here of encouraging a database owner and an application role. So let's look briefly at the other part of integration. We have this nice platform IAM at Zalando, which basically allows us to use JSON web tokens, so like 500-600 bytes of signed JSON to authenticate employees against systems. And we thought, okay, let's stop using passwords in Postgres too, because yet another password. Syncing passwords is hard. Connecting to LDAP from AWS is annoying. So in the end, luckily, Postgres, again, greatly extensible, supports PAM, and one of my colleagues, he wrote this module, so now basically we do the JSON web token verification from Postgres. We talk to some service that tells us this token is really valid, and if it's okay, the employee is able to log into the database. The neat thing is we basically get the Google MFA for free, so employees cannot get the token without MFA enabled. And that is also very convenient. One example basically here is this TED token. It creates a token for you and then you connect to the database. Let's go to monitoring quickly. Where's the minutes left? Am I supposed to? Okay. How does it look like, the setup in Kubernetes? Briefly, before Alexei goes into more detail. There is like a pod that's running Postgres. And there is one extension from Alexander Kukushkin, which is BGMon. It's basically an extension running in Postgres that gives us the REST API exposing pgstat activity. Why will you see in a few slides. And there is the Scala sidecar that streams all our Postgres logs into the cloud. And then we have pgview, which I will show. We have a Zetmon agent, which is our platform monitoring for long-time statistics. And we have the real worker, who allows teams basically to execute SQL code against the database for like KPI and other kinds of process monitoring. pgview, I talked about it. We have this REST API around pgstat activity, and basically what it does in the lower half, it exposes everything that is currently running, which is really helpful, so people can go to a web UI, look at all the Postgres nodes that are running and see what's going on in the database. There is storage, there is I/O and memory, and this was greatly appreciated when we rolled this out. Remember, there is like no SSH anywhere, so you can't go there and use the old nice terminal tool anymore. It integrates into the other monitoring with some nice set of deep links, so this is really helpful. People don't have to remember where to go for data. And in the end, we have basically Grafana and KairosDB for storing all the metric data we have for the recent 60 days. So everything you basically know about metrics is going there, like I/O, CPU, memory, whatever you can imagine. And we're also tracking this table sizes, sequential scans, index usage, and so on. Yeah, this is then basically my part. It was really fast, so this means you will get more technical stuff from Alexei in the next minutes. Are there any questions right now? Due to timing, I think I can take one or two quickly at this point. None? Great. Okay, then it's up to you.
Yeah, you can also ask your questions later. So I'm Alexei, I'm supposed to go into details on everything, and I'm going to describe a bit in more details our infrastructure, and also because we at FOSDEM, I'm going to highlight what we have in open source and how you can actually use what we have to build your own infrastructure. Yeah, so we are building this so-called cloud-native infrastructure, meaning that our services directly interact with Kubernetes, know about existence of Kubernetes, and can take advantage of, all the benefits that Kubernetes provides. So I saw a lot of hands earlier when Jan asked who knows about Kubernetes, but still I want to highlight why are we doing this. So we have one database. It's really easy to SSH into the database and then run initdb in case of Postgres, configure it and run it, and this is fine. If you have 10 databases, you probably start to employ solutions like Ansible or Puppet or Chief or something else that allows you to write scripts to once and then run them against your database cluster, changing perhaps the name, the database size, and some parameters. And this is also fine. But even if you have this, you still have to go to the system team, ask them to provision your server, and this goes for every database. If you have thousands of databases, you don't want to go to the system team for each of them. Instead, you want a system that will recognize your demands in terms of, for instance, CPU, disk size, and memory, and provision servers for you, and then run your databases on top of this fully automatically. What you need to do is to just declare your intention to do this using some human writable format like YAML, for instance, and then you expect the system to do this. Also, as Jan mentioned, we are running databases in containers. So what Kubernetes is the open source Linux container management system. It's developed by Google and Red Hat and many other contributors around the world. And yeah, it has a very rich metadata. Each object in Kubernetes can be tagged with the label. There are concepts of nodes and pods. I'm also quickly going through Kubernetes objects because this would be essential when describing how we use it. So node is your equivalent of a physical server. Pod is your application. Each pod can consist of multiple containers. Those containers share the network and the disk in a shared namespace. And pods are scheduled on the nodes depending on the resource requirements. So each pod can declare which resources it needs, and Kubernetes will figure out which node to run it, and then it can automatically provide more nodes if your infrastructure supports this. As Kubernetes can run on top of, for instance, AWS or Google Compute Cloud, which can provide service automatically. It can also scale up your infrastructure automatically as well. So we also have, so Kubernetes itself is basically a system which consists of a system node, actually 2 nodes at least, master nodes, and worker nodes. So system nodes provide all the system software, and worker nodes actually run your applications in the form of pods. There are also services and endpoints which answer the question of how do your application connect to your pods, to your database pods. There is a service that basically points to one of your pods, or maybe more than one, but in case of Postgres database, you really want, for instance, only a single master. And there is an endpoint that actually stores the address of the pod where your application should go if it uses the DNS of the service. And there is also stateful sets that are designed specifically to run stateful applications on top of Kubernetes, because normally if your pod goes down and there is a volume attached to that pod, the disk volume, then this volume goes down, and if your pod controller creates a replacement, then it gets a new volume and has to initialize the database in you, and if your database is big, that doesn't work. So people from Kubernetes invented stateful sets that allows to keep the attachment of volume and the pod together. So if your pod dies, then the new one gets respawned together with the existing volume, and that means that your data directory is still there. So for an example, there is a stateful set that defines 3 pods. Each pod asks for 100 gigabytes of disk space. Each pod mounts this 100 gigabyte volume as home Postgres PG root. And then there is a container inside this pod that starts. It does initdb on this home Postgres PG data when it is a container 0. When it's not a container 0, it does a PG base backup from container 0. This is how you basically get your replication. And then if Postgres dies, it just gets restarted by the stateful set. So we essentially get some sort of availability for free from the stateful set idea. So this is shortly about Kubernetes objects, and now there are multiple ways to run Postgres on Kubernetes once we settle that we probably want to do this. So bare stateful sets, this is the setup that I just described. There is a thing called Helm that allows you to automate writing YAML manifests and basically write only essential stuff in it. There are solutions based on the bot pattern. I will briefly touch what is it. And there is a managed service like RDS or Google database, cloud databases from Google, or many other cloud providers that provide database, Postgres, cloud-based Postgres solutions. So there are stateful sets. This is the simplest one. You get the stateful set, you get master pod number 0. If the pod dies, it gets respawned automatically by the stateful set, and that is basically it. There are many advantages in it. One of them is that it's very simple. You can use whatever Postgres image you need. It works with any of them. And basically, it's easy to configure the service that points to these pods. The service always goes to pod number 0 because pod number 0 is the master. There are also disadvantages that we also came in production. One of the disadvantages is if the master pod dies, it takes some time, up to a couple of minutes, for this pod to be recreated by the controller. And during these couple of minutes, your application is not available. And this might not be what you want or what you mean by high availability. In case of like heavy traffic databases, you probably want seconds, not minutes of downtime. Also, if your volume gets corrupted, which unfortunately also happens with EBS, you're out of luck. So you have to start anew, and if there is a master corrupted, then you have to do a manual failover and continue with, so do a lot of manual interactions in your setup. And it's also kind of hard to monitor because your pod might be running, but Postgres did not start on that pod, and you have to employ some additional services in order to detect this. So there is Helm, which basically mentioned here because there are some Helm charts in order to provision Postgres, but Helm is actually just a provisioning system. It does not have a separate way of running Postgres on top of Kubernetes, so you can use these stateful sets based scenarios with Helm as well. It just allows you to write less YAML files, so it's basically same as the other solutions. And there are managed database service. This is the quote by Kelsey Hightower, one of the well-respected developers in Kubernetes community, who says that if you want to run managed databases on Kubernetes, then just look at, if you want to run databases on Kubernetes, then look at managed solutions. So we basically read this quote, but we did not obey it. Instead, we still decided to run our managed solutions on Kubernetes. Why is that? We don't want a vendor lock-in. We want a lot of we use a lot of extensions, and together with our own extensions, and vendors usually does not allow you to install custom extensions there. There is no super user access, so something like pgdump-o won't work because it requires super user. You can use new versions of Postgres like alphas and betas, which are usually very stable and allows you to check new capabilities before the official release and perhaps find some bugs and benefit to the Postgres community, but usually vendors does not provide that. And if in case of patches, like security patches, you want to apply them as fast as possible and not to wait for the vendor to do this. And one of the main disadvantages, it's very, very expensive. It's rather more expensive than just running bare instances on the same cloud provider. So we have another thing. We have something that is called, that is implementing the bot pattern called Patroni. And why do we need this? Well, we need automatic failover. As I described, in case of the stateful set, if your pod goes down, then you have to recreate it. And this takes time. So instead, we want the system to automatically figure out that the pod is down and do the failover. And the automatic failover can be done in their own way. A lot of people are doing this in their own way. For instance, just doing two clusters, master and replica. If the master dies, replica gets promoted. But if the master is still there, but there is a network partition, replica gets promoted, you get a split brain. So this is not how you want to do this. You want at least a quorum to decide who is the leader. You want to learn what happens if the network is partitioned. You want to account for that. And you want to stone it. Shoot the other node in the head. So if your master gets demoted, you want this master to not start ever again as the master while the other master is running. So you want to avoid split brain as much as possible, for instance, by using the watchdog. So given that this is the schema of typical setup, we have a primary that is replicating to the secondary, and you have a quorum that is based on some consistency layer. In this case, this is etcd, a small application from CoreOS. So the master always pings the etcd and says, I am the leader, updates the leader regularly, and the replica regularly asks who is the leader, did the leader change? And if the leader changes, then the replica either initiates its own promotion, depending on whether it's the healthiest node around, or follows the other leader. And if the master gets partitioned, then it won't be able to ping the etcd saying I am the leader, and in that case, basically it gets demoted by itself. But unfortunately, Postgres cannot talk to etcd or systems like that directly. So for that, you need a separate daemon that runs alongside your Postgres installation and talks to etcd, both talking to Postgres, and decides at some time whether Postgres has to be promoted and demoted. And this basically is called bot pattern. And we have the implementation of this bot pattern in Python that is called Patroni. It's developed in open source by Zalando and contributors around the world. It's quite heavily used by quite big companies. And it supports etcd, console, Zookeeper, and it has recently been So recently, a support for Kubernetes has also been committed by one of our developers, Alexander Kukushkin. So Patroni can talk to Kubernetes directly, and if you run like multiple pods on Kubernetes, each of them using Patroni, it will use Kubernetes to decide who is the master and do automatic failovers in case your master has disappeared. So we use such a thing as annotations. It's inside the metadata in Kubernetes. So each pod has its own annotation saying providing some details about that pod. We have an endpoint that points to the leader. We use endpoints because endpoints are updated atomically. So there is a guarantee that you want that only one leader is there, and that another pod will not override the current leader because of the race condition. And we basically also use services to direct clients to the correct pods. So there is also a compatibility mode that allows to use config maps and not endpoints in case you are running in some systems like OpenStack that does not allow easy modification of the endpoint. And Patroni is packaged in the Docker image because Kubernetes is all about Docker or about other containers, but we use Docker. So there is a sphere that contains Patroni, multiple Postgres versions, some extensions, and it has a rather small size, so it doesn't take a lot to download it on your server before provisioning. One of the interesting things it also contains is the POM authentication for Postgres that I will touch briefly later. It's also open source, so you can get it in GitHub. And this is how we run one server. But the question is how we run thousands of servers, how we run databases as a server. We don't want to write manifests to provision each of our clusters, each of these thousands of them. Even if we have Patroni to do the failover, we still have to write those manifests. Instead, we have developed a Go application that implements a so-called operator pattern. So instead of doing typical DBA tasks by hand, we have a program that does this for us, which basically starts our databases, that maintains them, syncs Kubernetes objects, allows us to update configuration of this particular cluster, and, well, ultimately it can also delete databases as well. So we now use it for staging and production clusters inside Surrender, and I think some other people are using this. This is part of the Hackwick project by one of my colleagues, Murat Kabulov, and it's also open source. You can also get it on GitHub. So how it works layer by layer, starting from operator that starts pods with a Spira image and provides environment variables for Spira. Spira gets these environment variables and generates Patroni configuration. Then Patroni gets started, and then using the Patroni configuration, Patroni starts Postgres, figures out if it's the first node in the cluster, and if it is the first one, initializes the cluster. If it's not the first one, gets all its peers and initializes replication and continues running quite stably and does failovers if necessary. So this is the schema, basically how it works. The database deployer deploys the manifest. The cluster manifest goes to the operator pod. The operator pod uses the cluster manifest and its own configuration and something that's called infrastructure roles to create Kubernetes objects. Basically, it creates the actual stateful set with pods inside. Spira is inside. It creates the service to connect client applications. It creates the secrets so that passwords for the client applications are not propagated anywhere in the plain text, but read from secrets. I think Jan briefly mentioned this. And what the developer needs to know is only the small YAML manifest. This is how small is it. So basically, you have to provide a name, the number of instances for your cluster, version of your Postgres, and if you want, you can provide users and databases that operator will create it for you. And that is basically it, nothing else. You provide this manifest, and every developer even not familiar with Postgres can do this. You provide this, and we create you the operator. The operator will create you the Postgres cluster. High availability Postgres cluster with the amount of instances that you asked, and it will do automatic failovers for you. So this is the operator configuration. Each operator runs in the Kubernetes cluster and runs some configuration, like what is the Docker image that is used for all the Postgres clusters. Right now, we only support our own Spira image. We cannot work with stock Postgres image. There is something like infrastructure roles that, I will touch afterwards. Superuser username, replication username. How often do we go to each cluster and check that all Kubernetes objects are in place, that they are not deleted, and if they are not deleted, that we will resync it. There is an API port that you can interact with the operator and ask for the internal state of it for monitoring purposes. And there are some other details that I will touch later. So we also can create roles for you. And there are multiple roles. Some of them are described in your cluster manifest. Those are roles that will be created for this specific cluster. There are also such a thing as infrastructure roles. For instance, in your cluster, you want to monitor your Postgres pods, and for that, you need Postgres to have a certain user that the monitoring will connect to Postgres. And this user should be the same for all pods, and for that we have such a thing as infrastructure roles that gets injected into each Postgres cluster that is created by the operator. And how do we manage human users? We have such a thing as the Teams API. Teams API is configured in the operational configuration. You basically get a URL. This URL is OAuth protected, so you need a secret inside Kubernetes that contains the OAuth token, and this URL delivers you the list of members of a given team. A team is specified in the cluster configuration, and once this list of users is delivered, they are created in your cluster, and they are created in a special way so that you cannot authenticate using the password, but you can only authenticate using your OAuth token. So how does that work? We have a PAM module that is also written by Alex Kukushkin. It's open source, and it basically goes to an endpoint in OAuth and validates the password and token that the user supplies against this endpoint, and either allows you to connect to the databases or not. So essentially, it's equivalent to very long passwords. For us, I think our tokens are like 600 characters or something like that. And those tokens are expiring every hour. So you never had an issue that you have a password that never expired and the colleague went elsewhere and he's still in the system and can log in. So this is automatically expiring very long passwords. The only problem is not all Postgres clients support this. For instance, if you use .pgpass in your Postgres, there is a limit, I think, of 255 characters for the password. But if you use something like an environment variable pgpassword, then it will work. So it also can supply some arbitrary other parameters to the endpoint. For instance, you can also validate that the user is indeed part of the team that it claims to be part of. And it's configured in the operator configuration. So there is a PAM configuration that points to this URL where PAM should validate against. And there is the PAM role. So in pghba-conf, the operator adds this line, host SSL, all plus users. Plus means that the user has to be part of the users group. Then also all, so we want to cover all databases, all hosts, and PAM. So this means that those users that are part of the users group will get through PAM and will only be permitted if this PAM module allows them. So this is basically how we authenticate human users. And we also do something else from the operator. As I said, it's a replacement for your DBA. And for instance, we can dynamically change the disk size on when running on AWS. The operator runs on top of Kubernetes. Kubernetes is kind of platform independent. But in case you are running on AWS as we are, we can also dynamically change your disk size. So if you, in your manifest, say something like the volume size, like not 1 gigabyte, but change it after you deployed your cluster to, for instance, 5 gigabytes, then the operator will come to your cluster, call EBS API to resize your volume, and then get inside your every pod and run resize 2FS on the actual file system to make the file system aware of this resize. And you can grow your cluster for, well, almost for free. You have to still pay to AWS for EBS size. So it basically solves the problem of clusters running out of disk space. And we also support such things as Kubernetes cluster upgrades. Why do we need this? As Kubernetes is a very, very, well, relatively young technology, people needs, our system team need to keep in pace for the Kubernetes development. So Kubernetes is developed very, very fast, and they need to upgrade our cluster to the new version of Kubernetes also very often. But each upgrade means that you have to kill your nodes and then create new ones, and that is very disruptive for Postgres databases running on these nodes, obviously. And one of the issues that we came across is that when the node is killed, then Patroni will do the automatic failover if the master node, if the node where the master is running is killed. But this automatic failover may land the master on another node that is still the old one, that is still also requires to be killed. And that means that during the cluster upgrade, we may have multiple failovers, which is very disruptive for client applications that connect to this database because they have to handle these cases multiple times. So we try to minimize this, and we actually succeeded with the operator and Kubernetes. So we try to avoid multiple failovers, and for this, there is a convention that each node is marked with a special label that is configured in the operator, is the node readiness label. And when the operator finds out that the node readiness label disappeared, for instance, when our system team decides to rotate, to upgrade the cluster, a certain set of the nodes have this label removed, and then the nodes are drained, meaning that all containers from this node are asked to be deleted. And during this time, the operator detects that the node has to be decommissioned and finds out all master pods running on that node and moves those master pods to the node that is not yet, to the node that is healthy. Basically does the failovers to this master node of these master pods. And in the pods, we have a definition that pod can only be run on a ready node. We use the feature of Kubernetes that is called node affinity, saying basically that this pod can also run on the node that has this lifecycle status ready label in our case. And the operator also for each pod defines the pod disruption budget that says that if you have masters running on this node, you cannot kill this node when it's drained. So the Kubernetes lifecycle manager, this is our component that does all the cluster upgrades, essentially waits until the node runs out of all master pods before killing this node. And this is basically how we make sure that we have only one failover during cluster upgrades. So this is basically it. This is the list of open source applications that we have. Feel free to take a look, use it, and send your feedback. And if you have any questions to me or to Jan, then I will be happy to answer them now. Thank you.
So it's not a technical questions, but more on the human side. How much time it took you to build this solution and design it, and how many people were behind this?
So the vision for deploying Postgres on Kubernetes started January 2017. So basically Kubernetes came around and we made the decision to go there. The key part was this initial requirement that the whole deployment, including an application and a Postgres database, comes straight from Git. So basically nothing else, no UI in production, nothing, all from Git, then a deployment pipeline. And after that, I think we had the first working operator in March, and it was like 2 persons working on it, kind of, Oleksiy and Murat, from January to March to see the first production not production deployments, but the first Postgres deployments on Kubernetes. And the amount of features now, from volume resizing to figuring out how to do cluster upgrade, basically has grown until like autumn last year, I would say. With still basically 2 people doing the coding and the development.
Does your automatic systems also make database backups?
Yes, we basically Patroni acts with Wally, so we basically do Wally and ship like a nightly base backup to Amazon S3, and we do continuous archiving of all the wall segments to S3 during the day, and we store basically 5 days on S3 for every cluster we have. So this is enough basically when you wake up Monday morning, figure out you broke something on Friday, you can go back, and for other clusters where we need more, we can store more, yes.
And regarding the cluster, is it the standard Postgres streaming replication or
Yes,
something else?
yes. It's all standard streaming replication in Postgres. And we are now giving, like the latest feature we have is basically giving people this fork and clone, and this means basically in the manifest you can say, copy from this database at a given point in time, and this will basically enable other users and team without talking to us to trigger a point-in-time recovery to any system they are running.
Have you done any performance tests comparing to bare T2 or like some EC2 instances and Aurora serverless and something else?
No. So we are not, personally I'm not thinking that like every Postgres database Zalando is running will be on Kubernetes end of this year. Like I mentioned earlier, we have a lot of deployments using i3 instances because of high I/O demand, and Kubernetes doesn't support local storage right now. So if this changes, obviously everything goes to Kubernetes. But if we can tackle the majority of databases, like 95%, where we know from all the metrics we have that they're neither I/O demanding nor anything else, and this basically frees us from an amazing amount of work, and this is basically the goal of this. So the remainder we can still run on high-performing plain EC2 instances or whatever we need, basically. So we haven't measured this in particular.
Do you deal with multi-regions, or if
No,
so, how?
no. Which basically can still be done when you think about, we do recover clusters from the data center on AWS with S3 in the middle, but we just don't do it right now.
Where are your database clients? Are they also in the Amazon cloud?
Yes,
Okay.
most of them are. Let's say most clients are where the database are. So as you saw earlier, we have applications on Kubernetes, on plain EC2, and in the data center, and they are mostly local to the database, yes. I think I'm lying. I told earlier Alexi would answer all the questions, but he gave this micro away. That's fine.
Any advice for somebody running Kubernetes on bare metal that doesn't have that easy access to network volumes?
I'm supposed to say no. I don't know, maybe earlier I said we trust Patroni and Postgres streaming replication to run stuff in production on i3, which means like we lose volumes once a month and do a failover and we build a new replica automatically. Maybe this can help also in your basically local disk environment.
So basically running outside Kubernetes.
No, you have to basically trust that your pods and local storage lives long enough for Postgres to do the base backup and recover, and depends on your risk, I guess.
Okay, thanks.
Do you know that other people using your tools have experience running it on Azure or Google Cloud?
I'm told on Google Cloud, yes. We have also like a few contributors on the operator already. We have a few discussions and issues with people around Google Cloud. Azure. We have 3 more minutes for questions, I guess. And if there is more, we can talk outside, and probably we can also show some stuff if you're really curious, if we have been like just showing screenshots here.
In the beginning you mentioned that you have slaves which are running 1 hour behind the master.
Yes.
How do you do this?
I think there is a bash script wrapping the recovery command that just looks at time age of war file. So.
You can also do this built in Postgres, since I think 9.3 or 9.4 was a way of running Postgres clusters with streaming replication that are delayed against the master for a certain amount of time, just in recovery conf.
Great, then thank you for listening again. If you have any questions, reach out on Twitter, email. I think we're quite active and good in answering there too.